So to do the financial analysis, what we need to be able to do is to figure out what's kind of our annual cost associated with putting a component in like a capacitor bank. Because if I can't get a benefit stream from that cost, there's no sense in me doing that. And the way we do this for a lot of utility calculations is through the use of a concept called fixed charge rate. And sometimes I refer to that as FCR. Sometimes I might just refer to that as I. And so what the fixed charge rate is, and you can kind of read this with me here, it's basically the percentage of the total plant cost that's required over the project life per year to cover the minimal annual revenue requirements. And so if I take a cost of the capacitor bank, let's say it's $10,000, and if I have a fixed charge rate of 15%, then basically I multiply the 15% times $10,000, that I've got to have a benefit stream, at least $1,500 per year to justify me spending $10,000 on this capacitor. All right. So when I take that fixed charge rate and I multiply that by the total cost of the project, it gives us what we would call the annual fixed charges associated with that project. This is kind of a neat concept because what it does is it converts a capital cost into kind of like an annual cost, if you want to think about it that way. And the reason this is convenient is a lot of our benefits are actually calculated on a per year basis. So this actually gives us kind of a corresponding cost factor on an annual basis as well. Now, where this fixed charge rate comes from depends on a lot of things, but it basically kind of boils down to is what is the utilities cost of getting money, right? So what this is going to relate to, to get an FCR number, it relates to, well, what's going to be the capital recovery period for the amortization of the investment? Like, how long is this particular asset going to last? Is it going to last for 10 years? Is it going to last for 20 years? Is it going to last for 30 years? We have to know something about that. A lot of utility assets are good for maybe like 30, 40, 50 years. It's going to depend on the utility's cost of raising money. And so the way a utility could get money would be maybe, issuing stock. And so investors would have to have a certain amount of payback on stock investments. They'd expect a certain dividend in order to keep investing in the stock. Utilities may borrow money, and so that it would relate to the interest rate. If they have large projects, to what degree, that can they start charging or including that in the rate base ahead of time. It depends on the taxes they're paying. It depends on a lot of different things. It depends on what would be the salvage value of the asset. Could they recover some additional money out of it? Depends on their property taxes and insurance. Anything that relates to the cost of them being able to pay for this project goes into the fixed charge rate somehow. And for real basic projects, what you consider in here is like cost of capital, cost of taxes, the depreciation, the number of years this device is going to be good for. There's going to be operations costs associated with this. So if I got to go out and do inspections every year, we got to factor that in. There's going to be maintenance associated with this. All these things would actually go into the fixed charge rate. For an example of this, what I've done is I've just kind of copy and paste some material from this US Bulletin 1724D104, which is something that's issued by the US Department of Agriculture for use of rural utilities. And so what they've actually done in this case is they provided a spreadsheet that kind of actually formats all this stuff so a small utility could actually calculate their fixed charge rate to use this for making financial decisions. And so you don't need to know this in detail. I'm just kind of throwing this out there. Someday in the future, you might be working for utility. You might actually have to be doing some of these calculations instead of just taking this fixed charge rate as a given, right? You might actually have to come up with this number. And so for the utility, you have to know all this information, right? You have to know, well, what's like the net utility plant? This is what's sometimes referred to as the asset base. And this, for some utilities, this could run into billions of dollars. You'd have to know, like, well, how much stock has been issued. You'd have to know, like, how much debt is out there. You have to know what for your distribution system, let's say, what your operation and maintenance expenses are. What are your depreciation expenses? And that's going to depend on how long the equipment lasts, depends on your taxes. And given that you're going to have certain interest rates you're going to be paying, what you would use all this information for is to calculate this fixed charge rate. And so again, there's components due to debt and equity and taxes, depreciation, et cetera. And when you add all this up, this is where you get this fixed charge rate. So again, if you have a project, if you multiply this fixed charge rate times the cost of that project, what that does is it gives you the kind of the equivalent annual cost of basically doing that project, because you're going to have to borrow money for this, and see this, all this stuff you have to kind of work into this. Something else you would also do as well is you'd have to figure out, well, what are your benefits? What are the values associated with your benefits? And so you would have to then, into the spreadsheet, you'd put all this information in there. Is like, what's your annual energy consumption? What's your annual peak? And then you'd also work out, like, well, what are my factors as far as how to take this annual peak and convert that into like um, peak losses and peak kWh losses and things like that, right? And so anyway, again, don't worry about all the details of this right here, but just be aware that what you need to be able to do is come up with, say, for reducing kW losses, well, how much is this going to be worth in terms of like dollars per kilowatt of peak reduced, or, dollars per kWh reduced, stuff along those lines. And this just shows, some of these numbers kind of condensed down. And so you can get these in terms of dollars per month or dollars per year or whatever. But what you need to have is you need to have hard numbers for all these different benefit factors. So utilities will have all these numbers worked out. They'll basically figure out what their fixed charge rate is, and what are their various benefit numbers. And then if you're working for utilities, a distribution planner, then you take these numbers and you would apply these to different types of projects. So here's an example where what you're looking at is, you're looking at whether you want to spend money on building a new line, right? And so what you would be doing in this case is you'd be looking at your situation and what kind of impacts putting in this new line would actually have. And then what you would do is you would look at your cost of the project, and you look at the cost of the project on an annual basis. And then what you'd be doing is you'd be trying to basically figure out whether your benefits of actually doing the project, as far as the value of reducing kW and kWh, whether that's going to offset the cost of the project. So again, don't worry about understanding all this stuff right here, as I've shown here. Just be aware that this exists, and there's like accountants in the utility that are crunching all these numbers out. And if you're working for utility, you just don't, spend money on any sort of project you think is going to get a benefit. That you basically have to do a financial cost benefit analysis, and you have to show your management that any cost of a project is going to be offset by the dollar value of benefits. It's going to come down to a dollar justification. So as an example of something like this, just to kind of keep things really, really simple, let's suppose we had a fixed charge rate of 15%. And I've gone through some power flow analysis, whatever, and I basically found out that I can spend, say, like $8,000 on something like capacitor bank placement, to reduce annual peak losses by 10 kilowatts. And let's suppose our annual benefit's been determined to be that if I can reduce my peak losses, that's worth $200 per kilowatt per year. Okay, so that be a number that would be in the ballpark of what utilities would see as a benefit. So if I could reduce peak losses by 10 kilowatts, and that was worth $200 per kilowatt per year, then my annual benefit of putting that capacitor in the circuit would be $2,000 per year. Now, if that project cost me $8,000 and if the fixed charge rate was 15%, then the annualized cost of this would be $1,200 per year. And so from a real simplistic viewpoint, I mean, if you were going to have to make like a snap decision on this, what you would see is that your annual benefit exceeds my annual cost, and I would go ahead and probably do the project, right? It depends on what's going on with other projects because you're actually going to spend money on the ones that bring you the most benefits. But at least in this case right here, if you're going to look at this simple decision criteria, at least you can see it would make sense to go and do this particular project. You can make a cost benefit analysis argument to your management. So here's kind of an example of how this could be applied like to capacitor placement. So this is similar to the type of problem we worked before. Recalculate voltage drop and you calculate losses. And so we've got this simple circuit. We've got this data for the circuit. We've got load and we've got line impedances. And what we would want to do in this case is we want to put a capacitor in the circuit to improve the performance of the circuit. You'll do a base case first, so you find out where we're at initially. And then what you would do is you would figure out, well, what would be a good location for a capacitor in this case to improve performance. And then you would recompute all these metrics. And so let's suppose we wanted to get the power factor corrected to unity, and we want to use the half kVAR rule. Well, in this particular situation, what we would do to find our target value for getting unity power factor is we would add up the net load in the circuit. So I've got 3, 4, 5, 6. I got 6,000 kVA. And then given the power factor, I could figure out, well, how many kVAR capacitance am I going to need to have to get me back to unity power factor. Let's suppose in this case that the capacitance needs to be added in multiples of 300 kVAR because they have fixed sizes for these cans. Then what would be the size and bus location of this capacitance? And then I would recompute the voltage magnitude and losses and figure out if this is economically viable. And so we'll say the capacitor costs us $10,000. We have a fixed charge rate of 12%. And the benefit of peak loss reduction is $200 per kilowatt per year. So we want to know whether this is going to be economically viable. So we can start by doing the voltage drop using the K factor analysis, and we've done this before. We can calculate our initial losses, and we've done this sort of approximation before. And then if I take this value for Q, and if I multiply this by the reactive power factor, I see what I need is 3,180 kVAR of capacitance in order to get me to unity power factor. Now, if I'm stuck with 300 kVAR sizes, then I have to round off. And so what I'm going to do is I'm going to round off to 10 units. This is going to get me to 3,000. I probably want to be a little bit lagging as opposed to a little bit leading. So I'm going to go with 3,000 kVAR. And what I'm looking for is I'm looking for a location of the circuit. Now, if I want to apply the half kVAR rule, I'm looking for a location where I've got a flow of 1,500 kVAR. And so if I go to the circuit and if I map out my kVAR flows, what I see is I've got a place where my kVAR flow is 1,590 at bus number 2. All right. And so what I would do in this case, I would go ahead and I would put this capacitor bank in here at this particular location. And if I do that, if I put this capacitor bank here, and if I put in the size that would correspond to 3000 kVAR, then what I would do is I would go through and I do all these calculations over. Now, for the sake of looking at the voltage, I could do superposition. So what I can do in this particular scenario here is just simply look at the impact of putting a 3000 kVAR capacitor in. It's going to basically flow upstream to the substation through 2 miles of line. And so I'm going to get this increase in voltage as a result, which is going to cause a boost in the voltage at bus number 6. And then if I look at the impact on the line losses, and I have to look at the 2 line segments that are impacted by that change in capacitance. And so that's going to modify the line currents on sections 0, 1, and 1, 2. And when I calculate the new losses, this drops down to 248.3. So the net reduction in kW is pretty large in this case, is 63.9 kW. And so if the value of this is 200 kW per year, this actually has a pretty substantial benefit to it, where the annual cost is this total project cost times 15%, or 1,500. So $12,780 of benefit per year compared to $1,500 of cost per year. It's pretty simple. You know, you basically want to go ahead and add this project. However, what if we were looking at adding 2 capacitor banks and the benefit was only an additional 5 kilowatts of loss reduction? Okay, so I'm spending $10,000 more dollars times 15%. This is going to have a cost of $1,500 per year. My benefit, though, is going to be 5 kilowatts times 200, which is $1,000 per year. So now would I want to look at a 2 capacitor solution? Probably not, because when I look at the incremental cost, the cost of doing that, incremental cost of doing that project is more than the incremental benefit. And so this is why when you talk about doing capacitor replacement, this is why you don't see too many solutions that use many, many capacitors, because it turns out that you don't get that incremental benefit for the payoff. And generally the cost of a capacitor bank is pretty much fixed regardless of the size. It has more to do with the overhead and just putting that unit out there in the field. It's not really a function of the size of the cans, but the fact it has a certain kind of almost a fixed cost per location. So it doesn't really cost that much more to put out like a 3600 kVAR capacitor bank as opposed to a 3000. They're about the same in terms of cost. It has more to do with the location costs. So anyway, this is kind of the thought process you would actually go through when you talk about putting capacitors out in a circuit. I've got an additional example in here, which I'm not going to go over, which is pretty similar to the example I just did. It just kind of ties into some of these cases I was running for part 1 of this lecture. And so if you just wanted to see some additional detail, this is the second example in part 1. It's just kind of an add-in to kind of look at some of this economic analysis with the half kVAR rule. So for some additional references, if you want to get some additional material on just the mechanics of capacitor banks and what they look like, Tom Short in his book has some good chapters on that. For the VAR mile profile approach to analyzing this, a good reference for this is a book by Lee Willis on power distribution planning. It's actually a reference book. It's out by Marcel Decker. And then the paper that Granger and Lee wrote on the half kVAR rule is referenced right here. So if you go to the library and you go to library resources and you choose something like IEEE Explorer, which enables you to go through the IEEE database of papers, then you could actually find this paper and you can actually download it. So it actually has the, I guess, the proof behind this half kVAR rule. All right. So we're kind of come to the end now of our conventional steady state analysis for distribution systems. And now we're going to be looking a little bit more at operational problems and some more advanced smart grid functions. And what we'll do in the next lecture is we'll start looking at short circuit calculations, which is still a steady state calculation, but it's something we need to do for power system protection. Okay. So we'll cover the short circuit analysis in the next lecture then.